Uh, Good morning. Today is October 18th, and we're going to complete chapter 1. And I don't know if there will be some time to start chapter 2, which is related, it's very similar, but now instead of having aligned forces, we're going to have lateral forces, and that the result of that is bending. So we're going to go work similarly with finite elements defined by two joints, but in this case, the load will be lateral. So we're going to have bending. Okay, so that's chapter 2, which is also extremely important. Okay, let's pick up where we left last class. Oh, Jesus. Can you see my PowerPoint, Isaac?
Yes,
Oh, no. Okay, let me. Okay. Here. There. So this is something that we did. It's very simple discretization, one element. But in this case, what we did was we considered a distributed load. Of course, that means that there would be some error because the result, we know it's a quadratic distribution for the displacement. Okay, in this case, W, little w, that's for weight per unit length. So what we do is we take half of that and put it in here and the rest down here. So inside the element, there is no load.
okay.
And that's, we have to do it because our case is just discretization. So we're going to be worried about this and that
Doctor.
points.
So
Yep.
click on display setting.
I did it. Now?
Yep. Okay, now it's correct. No,
Now it's correct? Okay, good. So
no, doctor.
it's incorrect.
It's incorrect now.
How about now?
It's
No?
bad. No.
Okay, let me stop. Let me. Some people laugh at me. Good. At least you're in good shape. Let's see, share screen. Here it is, there. You can see now probably the PowerPoint, right?
Yes. Doctor.
Okay, now let's expand it in here. And let's swap. Let's swap. Tell me, talk to me.
Now it's good.
Okay, thank you. So I was saying that we have this case. So remember, this is the system of equations that we try to solve. In this case, in any case, we have n equations. So we have to have n unknowns. Okay, in this case, this point doesn't move, so the displacement is 0. And also in this point, the force, the reaction is unknown. So in this point, we have two external actions, okay? Half, in this case, half of the weight here, and the reaction. Positive is downwards in this case. And now, after we have applied one geometric boundary condition, we took the singularity out of this system and we can solve it. Remember, first, we're going to say a couple of words about this. First, we take a subsystem composed by equations with unknown displacements. So that's going to be the second one. Okay, so this 0 multiplied by -1, this multiplied by that, and this is what we get, we look for. So we take this point to the other side, and this is what we have. Okay? This is what we know for the displacements. Okay, so this d1x, we knew as a condition. So right now, here, all displacement are known. Now, the last step is to solve this system of equation is to multiply. We say we solve with the second subsystem, but what we really do is we multiply the vector of displacement times the stiffness matrix. And the result is going to be this. And here, this is what we do not know. So we take this term to the other side, and this is the result. It makes sense, because that's the external force, that's the reaction, and points in the negative direction upward. So that's the general process. Okay, and then this is the displacement for this point, and this is the assume people. This is an assumption, okay, for the displacement in this element. In this case, it's one single element. So this is the result. So we see that at x equals 0 here, it doesn't move. And then as you go to the other end, this displacement increases linearly. Okay. Now, the analytic solution, that's easy. That's a second order differential equation. Two boundary conditions, it's a second order. One condition on the left, one on the right. Remember, this is the fact that we have no load here. So there is no load in this end, it's a free end. So the stress and the strain are 0. That's what we mean. We can integrate that, and that's the result. That's a quadratic. Okay, and here, this is linear interpolation. That means that the solution is not exact. That's error. Okay, now we can evaluate that in the end at L, and this is the result. And you see that that's the displacement at the second joint. And this is exactly this one. So we see that we recover the solutions at the joints, but in the intermediate, in the domain of this element, there is some error. So this is the analytic solution. It's a quadratic. This is the finite elements approximation, linear. Of course, it's a good difference inside. Okay. So we have to be careful, because finite elements is an approximation. Okay, so let me insist on this, saying that this, we have to be careful, because if the load this is distributed, then when we integrate, we're going to get something here which is different order than linear. So this is the finite element approximation, linear. This is analytic. So there is a difference, there's an error. Okay, and the error is because we assume the linear approximation. So you want something different, then what you have to do is, between other things, you could try to partition the domain in more than one element. And this is what we are going to do. Well, I'm sorry, before we go to that, to judge the possibility of failure, we evaluate stress. So in the case of finite element, okay, the strain is constant in each element, because the U, the displacement, is linear. So the derivative is a constant. In the case of the analytic solution, it's linear variation. Okay, so that means that it's going to be a big error. Okay. So what can we do? What we can do is we can, instead of considering one single element, we partition in two elements. So this is element 1, okay? This is element 1, and this is element 2, there. So this is join 1, join 2, join 3. So in this case, this is the system of equations, okay? So this is something that we have done in class. So we see that in here, this part here belongs to element 1, and this part here belongs to element 2. That's why we have a 2 here, because in that point we added the contribution from each one of the joints. Here, this is the boundary condition. It's a geometric boundary condition. Because this is geometric boundary condition, we could solve. Okay, this is unknown. So that's 1, and we have 2 displacement unknowns, so we have 3 equations, 3 unknowns. So this is the first subsystem. Okay, we're going to say that something about this in a minute. So we take this part here, these 2 equations, and we put it down here. Okay, so we have this 0 multiplied by -1 by 0, and then we have these 2. So this part here is are these coefficients. On the left, these 2 unknowns, and on the right, 2 unknowns. We could solve this easily, and then we go back. Right now, you see that this is the displacements of every joint, and it's completely known. See the 3 values we know. We got 2 here, and the first one is a condition. So what we do is we multiply this vector times this row. So the 0 times 1, this times that, and the result has to be equal to this. In here, I have 1/4 of the weight here, and the reaction that we try to determine. And from here, we can, again, we can calculate the reaction. This is the reaction. And it's correct again. Okay? We can go on. Let me erase this. Okay. It looks like the animation is incorrect, but this is the solution. So we have from here to here, something is wrong. Doesn't want to work. That's element 1, and from here to there, it's element 2. Okay, so this value here is what we found in the previous. This is 2x, and this is the 3x, and this is the 1x, and that's 0 because that's a condition. We can do the same thing. So we can say that for every element, remember that epsilon x is equal to du dx, and it's going to be the second joint minus the displacement of the first divided by the length of the element. So since this is constant in every element, we see that this is the approximation finite element method. And this is the analytic. It's getting close, but it's not the same. This is the correct. So we see that the displacement are exact. The distribution of stress is not. Okay? This is exact because when we replace the weight of this, because this is a uniform, into this, statically is equivalent. That's why we get the exact values of the displacements. But in between, no, we have an error. Okay, so we have to be alert on that. Okay, finite elements is a good method, very extremely good method, but it's not exact. We have to be smart enough in order to use it effectively. So I'm just repeating. Hopefully, that will be helpful. Now, this other example, where you have to review it at home, I'm just going to comment. Let's suppose that we have this case. In this case, you see that this and this end develop reactions. This is a reaction 1 and a reaction 2. So this example is indeterminate case. Okay, but we can solve this also using finite elements. Okay, in this case, this is the discretization, and we see immediately that this point doesn't move, this point either. So we only have one displacement unknown for the first subsystem, and then we can have to calculate the 2 reactions on the ends. Okay, that's for element 1. In this case, I insist that this is L. So this is L of the first element. And then we can do something similar for the second element. This is L for the second element. It looks like the EA, it's a constant section, so this EA term is the same for both elements. Again, this is something that we did. The equilibrium of every joint. Here, we have only one element here, so the external force is just this. In this case, this is different in this joint, okay? So this force here, this 6,000, okay? Part of that is going to be applied for the equilibrium of this element, and the rest will be employed in order to equilibrate the second element, or yes. That's what we're saying here. In the third one, this force here, the external force, is used to equilibrate the second element. That allows us to integrate all elements in a system. That's something that we do all the time. This is the system of equations total, and you can see immediately again the situation. This is the first element, and this is the second element. Of course, you have a combination here in this common term. This is boundary conditions. So we see that we can take the second, this is the equation where we include the unknowns. So we can take it down there. So that's the equation, okay? So on the left here, you see that this is the force at the second joint. So the force is this 6,000 pounds in this case. This is 0, so this in that term doesn't appear. And the central one is here, okay? So this is EA. This is the combination multiplied by D2. And on the other side, there's 6,000. This is the handling of the units. And of course, we can calculate D2. Positive, meaning that it moves to the right. So you have to review this in detail later on, okay? And then there's the second subsystem. So this is the first subsystem, and this is the second subsystem. So what we have to do is we have to multiply right now. So D1, D3 are 0, D2 is this thing, so we know this vector. So we can multiply by the first and by the third equations. We can get the unknown forces, external forces, which are the reactions. we see that this value is larger than this one. It makes sense because you are applying a force closer to this end. So it makes sense that expect that this reaction be higher than this one. At the end, when you are very close to this end, basically this point of support doesn't work. Most of the load is going to be taken by this support. So makes sense. Again, for each element, we have to do this analysis, okay? This is the first joint of of each element, second joint of each element. This is the interpolation that we assume, okay? So for the first element, okay, we know that the first joint, we're talking about this element. So this point here, this joint, see, doesn't move. So D1 is 0. And D2 is this value that we obtain. The length, it's 20 inches here. For the second element, okay, so this is the second element. Okay, this is the first joint of the second element, and that's D2. So that's the value that we calculated. And the second joint here, this is the second joint, doesn't move. Okay, so we can develop the interpolation, and this is what we obtain. We go from 0 to D2, and the second element, we go from D2 to until 0. Okay, so we see that there is continuity here because we established that D2 is the same for both elements. Again, after we have solved, we have to go one element by one. So this is the strain. So this is the displacements of both joints, the second and minus the first, divided by the length. So that's that, and we see that this result is positive. So that means that we apply this force to the right, this element is in tension. For the second, we have here the values of the first and second joints. We replace it here, and the result is going to be negative. That means that it makes sense, right? If you put the force here, move it to the right, this is going to be in tension, and this is going to be in compression. So it makes sense. What we are doing is analysis. We are not describing. See, when we conclude that makes sense, that's analysis. Okay, this is okay, so far, is there any question, people? Is there any question? Let me, Isaac, is there any question from anybody?
No, doctor, there's no question.
Okay, people, okay. Okay, now, this is the example that we started last class, okay? And the big difference now is that you can immediately see that each element is not aligned with the others. So every element, in this case, I'm using 4 elements, okay, has a different direction for its local reference system. And the only way we can solve this is that we take components in a common reference system. That's what we call the global reference system. Okay, so everybody will be talking the same language. Okay, so we have to do this conversion. And that's what we do when we convert or we transform from the local to the global. Okay, for example, this is the This is the first element, okay? This is the first element. So this is the element that goes from join 1 to join 2. In this case, okay, this is the global reference system. So this is theta for the first element. Remember, please, this is very important. This is theta positive. Okay? So that's why we said positive 45. Now, with these values, okay, we could develop the stiffness matrix of this element in this reference system, in the global reference system. We have to do that for every element. Now, what else? We see that this join here connects element 1, element 2, and element 4. So this point here, it's the displacement in the x and in the y direction are the same for all of these three elements. Similarly, the force that I apply here is to be splitted. And one part of that will be taken by element 1, by element 2, and the rest by element 4. Okay? So again, here I have an external force. That external force is going to be divided into a piece that will be taken by element 1, by element 2, and by element 4. Similarly for the joint 4 and for joint 3. Nevares, do you have a question?
Yes, doctor. Good morning. Does the exercise give you the area of each element?
Yeah.
Okay.
Yeah, it's usually the data. Or please remember that in general, that's a characteristic. Okay, if you analyze something, that means that you are given this value. If you try to design something, that means that you have to find it. And in that case, what you can do is you can try a value, calculate, and then check if the stresses and the displacements are good enough. If the stresses are very high, what you have to do is you have to increase the size of the element, the area. And that will reduce probably the stresses. So that depends. But in general, that's a geometric characteristic. That depends on the depth of the problem. Okay. So this is what we call the table of connectivity, okay? This is what we call the table of connectivity. Here in this chapter and in chapter 2, we're going to be interested in this information. When you go up to and use ANSYS, you don't have to worry much about it, except that this word connectivity is very important. Okay, for example, it may happen that you connect element 1 and element 4 and don't connect it to element 2. That's an error. That's very common, right, Isaac?
Yes, doctor. The connection is very important.
It's very important, okay? So even though you don't have to prepare this table, you have to be certain that if you have a connection here, you better be certain that the three elements or whatever number of elements in that point, they do indeed connect between them. Okay, let's go on now.
Doctor,
so,
could you please repeat the last part about the connections to be certain, please?
Yeah, what I'm saying is that when you go and start using a program, ANSYS or any other program, okay, you have to be certain that if you want to analyze this structure, okay, in this point, these elements connects to this element. Now, it can happen that you have this element, this cable. This element is different. So you have something like this, right? And by error, Okay, you see that there is very close. They are not connected. And for example, let's see that you connect this with that. And oh, Jesus, it's Monday. Okay, so you draw this point, this point, this point, and this point. And there are some cases when the program understands or doesn't understand that this end is the same as that joint and leave these 2 points not connected. Okay, so when you apply a force here, okay, this element will develop no stress. Okay, so what we're saying is that you have to be certain that when you have these points of connections, you have to check that they are really connected. That's what we're saying. Okay?
Doctor.
Yeah, so thanks.
No problem. Yeah, there's another question?
Yes, doctor. I am Alex Valle. Good morning.
How is Ambato?
Why the element 4 don't have the angle? Why?
Because you have to find it. You tell me, how much is the angle of theta 4? Or yeah, theta 4. How much is theta 4? So you see that in this case, I'm defining element 4 from joint 2 to joint 4. Okay, so element 4, let me see, goes from here to there. So this is the direction. This is the local reference system of element 4. So in this case, this is global X, this is local X. So the angle would be from here to here. So this is theta 4. Now, I'm drawing this angle in the positive sense. Okay, so how much do you think it's going to be this value, theta 4? How much do you think it would, Mr. Wacon, are you here? Mr. Wacon? Mr. Wacon?
Yes, doctor.
Can you guess a value for theta 4, more or less? Can you?
Yes. Minus.
No, it's positive. I'm drawing this as a positive. Please remember, this is the system X, Y, this is positive Z, counterclockwise. And I'm drawing from here, which is the horizontal X-axis, global axis, from here to here. So I'm drawing in the positive direction. So right here, theta 4 is positive. But I want you to guess a value for theta 4, more or less.
316 minus angle the element 3, or not?
Yeah, could be. For example, you go from here, that's 90, 180 to 70. So it's going to be, yeah, probably it's a little bit more than that. So 300 or something like that. Positive.
Yes.
Positive. But this angle is the one, corresponds to this one here, right? But in this case, if you take this one here, that's going to be negative. So let's suppose this is 310, and this is going to be 50, minus 50. So it's going to be the same. Okay, so theta 4, this is going to be approximately equal to 310 or minus 50. More or less, okay? If you have the positions, you can calculate this exactly. Okay, people, can I go on? Okay. So for each element, we do this. But we have to remember that this is the local reference system. Okay, so in this case, for this element, we are saying is that this section moves in a local x direction. For this element, this section moves in the local reference system. So this is U. Let's see, local. This is U local. For every element, we can draw how much this section moves in the x direction. This section moves in the x direction. For every element, we have to do it. And we assume that for every element, this variation along this x-axis is linear. Okay, so from each element, again, we can develop these calculations. So the strain is going to be constant, and the stress is also going to be constant for every element. And then, there was a question?
Yes, good morning. About the displacement function, there is a way to form a single displacement function, but in the case when we have a linear bars element, or it is necessary to separate the function for each element. For example, in that case,
You have to do it because in general, for example, let's suppose I have something like this. You see that immediately, you see, I can put 3 joints to analyze this problem, right? And then you can see that you have an EA over L value for the first element and a different EA over L element for the second one. So what is going to happen is that this local and this local, they coincide in direction. But you have to set up a linear displacement for this one and another linear displacement for that one. Both are linear, but the values of the resulting values are different according to the motions or the displacements of the joint element, of the joints of this element.
so we have set up displacement.
You don't have to. Please, because try to be flexible in your mind. Okay. Remember, you're going to be an engineer, and you have to use your judgment. You don't have to, because that means that every time you're going to do the same. No, that depends on the situation. So what I'm trying to teach you is that you have to do this analysis. You have to consider the limitations of the process. Now you have to consider, you have to have in your mind how these things are handled inside the computer so you can use it effectively. So when you say, I have to do this, no, that depends on the situation. Go on.
My question is about if we must do or set up the displacement function for each element when I must graph the
Yeah, well, that depends on the calculations that you will need. For example, let's suppose that I want you to calculate the stress. Okay, in that case, you determine the displacement of every joint. Please, this is very important. These calculations are in the local reference system. All of this is local. And when we solve this, we solve it for the global displacements. So from the global, we transform into local, and from local, we calculate strains and stress. Now, if you need to plot the displacement of this, yes, you have to do this. But if you just want the stress, that's all what you need. You don't need to plot. You need to do the interpolations. That depends on the problem that you are trying to solve. Okay? But here, for example, this point, probably if you apply a force downwards, this point will move like this, probably, and also will move downwards, right? So this point will come here. Damn it. So this cable will be about here. This will be about here. This point also move downwards and to the right. So we'll go like this and like that. So you're going to have something like this. And this is going to move like here. Okay, so, but we know that in every point, see, for example, this section here moves in this direction. That means that this section here will be about here. So if it originally was here and now it's here, that means that there's going to be an elongation. And that's what we call U. That's a displacement in the local X direction. Okay? Mr. I don't know your name. The person was asking.
Ordóñez. Yes.
Did I answer your question, Ordóñez?
Yes, doctor.
Okay, I'm glad. Okay. Please try to be careful with these things, okay? This is local, okay? And when you say global, there is no hat. Now, once we have determined the position or the angular position of each element, we can go on and calculate the stiffness matrix for every element. For every element. And this matrix relates forces, external forces, and displacements. But now the components of these forces and moments are expressed in the global reference system. Okay? So that's the beauty. Now here, when you see a big C or a big S, what we mean is that it's the cosine or the sine. But I wanted to save some ink. That's why I just write it like that. And for example, this is the matrix for element 1. So this is relating this and that joints. Okay, so what I'm saying is that these rows, they relate F1. I'm writing as a vector. That means that I have two components in X and Y. And this is multiplied by the displacement of the first zone, so joint. So this is vector 1. The second row, oh shit, I made a mistake. Yeah. I included only one. Okay. So D1 is both. And the second part you see here is related to the second joint. Okay, so this means that this is the part of the external force which is acting here, which is applied to this element. And this is the force that we need in this point in order to keep in equilibrium this element. The problem with this joint is that here there are other elements which are connected in that point. So what we have to be is we have to be certain that when we have these situations, okay? The part of the external forces, for example, this F2, this is for the first element that we take, okay, to equilibrate this element has to be consistent with this, the part of this force which is taken to equilibrate the second and the fourth element. In this case, we see that the external force, F1, how much is the external force here, people? How much is external force?
It's
How much? It's zero. Yes, it's zero. Because there's no external force here. That means that if we have a force to equilibrate this element, and I have another force to equilibrate this, and another for equilibrate this, between these three, they have to cancel. And that's why how we establish one single global stiffness matrix. Let's take a break. Okay, and when we continue, we can solve this thing, and I'm going to explain a characteristic or a way, because in this case, you're going to see that the number of equations is a little bit large. So when you have to solve the system, what you have to do is you have to take a subsystem, but the problem is that when you try to implement that in the computer, that's messy, very messy. So there is an option for that, much, much simpler. I'm going to explain that. So let's take a break now.